parameters, you can get a closed loop transfer function in this form. So this is the closed loop transfer function of the domain of the system. Okay. And so the denominator are all stable. Okay. So it's because it's a closed loop system. Okay. And the numerator, look at the numerator. Numerator, two terms you can see. One is quite small, so it's a stable, the 0. Another one is close to 1, so we consider this as non-cancelable 0. Okay. So we choose these two. One is what we call stable part, stable 0. Another is unstable 0. Okay. And go back to here. This is the zero-phase error tracking control. This one. This one. So the A part is used to cancel out all of the stable poles. And the BCA, this part, is to cancel out the stable 0. And this one is to cancel out the phase of the unstable 0. And this constant is to compensate for the 0, the BC gain. So we have the pole here, and the BCA. These two can be cancelled, and this one we need to cancel the phase. In order to cancel the phase, we use the complex conjugate part, like this one. Okay. And again, this gain will be used to make the DC gain become 1. So the overall zero-phase error tracking control is like this. Okay, like this. Okay, you have this one, you have this one. Okay. And this part is from the originally pole and stable 0. So overall, it's like this. And the D, in order to implement this, we need what we call look at F actually. Look, we need the non-causal input from D and S. D is actually the relative degree of the original closed loop system. And S is from this part. This is S. Okay. There's a 1. In order to cancel the phase, we need one step further. So D is 1, S is also 1, so it's 2. You need to provide your command 2 steps ahead. Okay. Any question? So this is for the zero-phase error tracking control. And if you can see the simulation results, I want you to have some feeling of this. So the starting line is the original command. We want to track this. And the dash line here is the output response without the feedforward or without zero-phase error tracking control. So you can see very clearly that there are tracking errors. And this one represents the one with feedforward zero-phase error tracking control. So it's very close to the connect. Only as these few places, these places are very close. Okay. And if you compute the tracking error, you can see the one without zero-phase error tracking control has larger error, especially at the steady state. And the one with tracking feedforward control is very small. Okay. The errors are very small. And for problem number 2, we want to design a so-called disturbance observer. And the requirement of the disturbance observer is that the external disturbance has bandwidth 10 radians per second. And the noise is larger than 100 radians per second. Okay. And our system bandwidth for the velocity loop is 10 hertz. And the bandwidth for the collision loop is 2 hertz. Okay. So we want to design the disturbance observer based on this requirement. So the disturbance observer. So basically, the disturbance observer should be implemented in this format. In this format, in the velocity loop. Okay. So you already have this, the nominal plan, and you want to design the Q filter here. And the Q filter should be designed. Q filter should be designed as a low-pass filter. And the bandwidth of this low-pass filter should cover the frequency range of disturbance. And it should be outside the frequency range of the noise. So these are the requirements. So our disturbance has bandwidth up to 10 radians per second. And the noise is larger than 100 radians per second. So the Q filter, the bandwidth of the Q filter should be between these two. Should be between these two. Okay. So the low-pass filter, we choose the cutoff frequency of low-pass filter is 10 hertz, roughly the same as our bandwidth of the each actions. 10 hertz is how much? 10 hertz is about, you multiply by 2 pi. Okay, 2 pi is about 6.28, right? And multiplied by 10, so it's about 60 radians per second. So 60 radians per second is roughly between 10 radians and 100 radians per second. So between these two. Okay. So you can choose Q filter like this. Okay. And the frequency response of the Q filter like this. So you need to implement your system like this. This should be the nominal plan include these two. Okay. Nominal plan. Okay. Nominal plan here is this one. Okay. And in our system, this one include the controller, what we call the the velocity loop controller. So this one. Should put it here. Any question? Any questions? So this is homework number 3. Any question? Okay. If no question on the homework number 3, let us continue our discussion on the S-type acceleration deceleration. Last time we discussed this. Okay. And we want to, for most cases, we want to design the so-called acceleration deceleration, meaning that we want to choose the parameters for this acceleration deceleration. Okay. So there are 4 parameters for this. Okay. Represent the acceleration parts and the deceleration parts. Okay. These 4 parameters we want to choose. And in some CNC commercial CNC controller, in order to simplify the design and to make the user easy to tune, most of them has what we call the impose the condition that all of these 4 parameters are the same. So you just need to choose one parameter, which is called, for example, time constant or some time parameter. That will make things much simpler. These are what we call completely symmetry. What we call symmetry S-type or S-shape acceleration. And some other will relax a little bit. Okay. This one will be the same as this one, and this one will be the same as this one. Okay. And this is what we call also symmetry. In other words, acceleration and deceleration are symmetry. Although this can be different from this one, but this one is the same as this one. The inner part, this one is the same as this one. So this part is the same as this. This is the same as. So it's symmetry. Symmetry. Okay. So in this case, then you have 2 parameters. Okay, you have 2 parameters only. Okay. But here, what I want to show you here is that because the length you want to travel is given, is limited, and the actuator has limit. So you have the maximum feed rate, you have the maximum acceleration, you have maximum jerk. It's limited. In this case, it means that these parameters cannot be arbitrarily chosen. In other words, some parameter cannot be feasible. If you arbitrarily choose this parameter, they may not form a so-called S-shape, acceleration, deceleration. Okay, what does this mean? Let me give you an example. For example, the distance is very short. This is very short. Within this short distance, you want to complete the whole acceleration, constant speed deceleration may not be possible because it's too short. Before you accelerate to some distance, you already finished. Maybe, in other words, the area under this should be equal to the length L. But because the length L is too short, you cannot find any part of this that can form a complete S shape, acceleration, deceleration, so that the area equals the sheer number of distance. Okay, that is in other words, the acceleration is limited, velocity is limited, jerk is limited, so that you do not have that much, that high acceleration that can reach there. Okay. Let me give you another example. For example, I want you to go to the family mark in 1 second. Can you do that? You cannot do that. If I want you to go there in 10 minutes, yeah, it's possible. Because you can consider yourself as an actuator. I can run. But my running speed is limited. My acceleration is limited because my energy is limited. And you are younger, your limit is larger than me. So you can reach there with much higher speed, much higher acceleration. Okay, so under some conditions, you may do it, I may not be able to do that. But under some extreme conditions, nobody can do that. We want to go there in 1 second. Can any one of you do that? 1 second. Go there. No way, right? So because our actuator has limitations. Okay? Yeah. So because of this, you cannot arbitrarily choose them. You can only choose them under this constraint. Under this constraint, there are some range that you can choose, but not every arbitrary parameters, time parameter. Okay. So in order to understand this, last time, from the definition of this, I have shown you that the parameter need to satisfy these inequalities. Okay? These are the inequalities that you can choose. Okay? These are the inequalities you can choose. In other words, if your parameter violate this inequality, then you cannot fulfill the so-called S-shape, acceleration, deceleration. Okay? Any questions? So let us look at this. Okay. And for the total length, it involves 4 parameters. Okay. For the so-called velocity and acceleration, they involve separate. They involve the acceleration part and deceleration part separate. And one more thing I want to emphasize. These conditions are what we call necessary conditions. In other words, your parameter must satisfy this condition in order that you can have the so-called S-shaped acceleration deceleration. You must satisfy that. But these are the necessary conditions. In other words, you must satisfy this in order to have S-shape. But even though you satisfy this, does not mean that you can have a complete S-shape acceleration deceleration. So these are you can consider these conditions are as a minimum requirement, necessary condition. Your parameter has to satisfy this. But even though your parameter satisfies this, does not mean that it's feasible. It's feasible because these are only necessary conditions. And last time, the derivation has shown this. The class note. Class note is where is that? Class note is another folder.
Yes. Yes, bro.
Yeah? This one?
It's within the motion control. You need to go into motion control.
Okay.
Break drop down.
Oh,
yes.
this one. Okay.
And the last.
Okay. Right? Look at this. And TS1, TS2. Okay. You see? TS1, TS2, let me see. Okay. This one is from what we call the constraint for the maximum acceleration. Okay. This one, we add these two together, so that we have this one. From here we have this one. But actually, so this inequality is from this inequality. F is from this inequality. Okay. Their summation less than 2JF. But actually, we require each of them less than JF. So this is a conservative condition. In other words, even though you satisfy this condition, does not guarantee each of them less than this. For example, this is a 1.5 JM. This is 0.2 JM. Their summation is still less than 2 JM, but this one violates the Joule limit. So it's a conservative. So this is a conservative condition. You have to remember this. Okay. But the idea I want to tell you is that the point I want to make is that the parameters cannot be arbitrarily chosen. You have to understand this because of the limitation, or because of the constraint, because of the length is limited. Okay. So let us look at this. This is we have actually here for these 4 parameters we have 5 inequality to satisfy. This is 1, 2, 3, 4, 1. These 5 inequalities we need to satisfy. But 4 parameters in the parameter space is 4 dimensions. It's difficult to analyze. So let us simplify it further. This inequality also implies this inequality. Right? In other words, the 4 of them must less than this. Also means these 2 must less than this. Right? Right. So this is also conservative. Also conservative. Okay? In other words, these 2 less than this does not imply they satisfy this. Okay? But at least if we simplify this to like this, and also imply that last 2 is also less than this, then we can separate this. We can simplify the constraint into involve only TS1 and TS2. Okay. So this one, this one, this one. We have 3 inequality for 2 variables, TS1 and TS2. Okay. TS1 and TS2. Okay. So we can look at this. Suppose we call this alpha, we call this beta, and call this gamma. And there is another number, we call it beta. Involve gamma and beta, call it beta. Anyway, in general, we need to satisfy these 5 inequalities. And in order to have a well-defined S-shaped acceleration deceleration, these 5 sets, the intersection of this must be non-empty. Non-empty. But it's too complicated, it's 4-dimensional, so we simplify it into only 3. In other words, the intersection of these 3 sets must be non-empty. These are the necessary conditions. Okay? So they can do like this. From the viewpoint of geometry, this x-axis is TS1, this is TS2. In the parameter space, TS1, TS2. Okay? And we have 3 conditions: C1, C2, and C3. Okay? C1, the boundary of C1, boundary meaning equality, right? The boundary of C1 is a straight line, and is what? 45 degrees, right? And the boundary of C3 is also a straight line, and the slope is what? Minus minus 1/2, you can say. This is TS2, right? This is TS1. So you can consider this as YX. Y over x is minus 1/2, right? So it's like this. The slope is like this. And this one is a hyperbolic curve. So it's like this. Okay? And C1. So C1 is like this. So, for example, suppose they are in this tape. The condition of C1 meaning that the parameter need to satisfy larger than this. Okay? Because it's a greater than or equal to this. So it's larger than this. And C3 is smaller than this. So C3 is smaller than this. So the intersection is of C1 and C3 is this region. Oh, by the way, remember there is an implicit inequality. The TS1, TS2, all of them are positive. So we look at only the first quadrant. So actually, we are looking at this region only. Okay. So actually, in addition to these 3, there are two more. One is TS1 greater than 0, TS2 greater than 0. But that is easy, so we don't need to consider that. Okay, we just look at these three. Okay. So C1 larger than this, C3 larger than, and C2 is this hyperbolic curve to be larger than. Okay. So suppose C1 and C2 do not have any intersection. C1 and C2 do not have any intersection, like this case. Then C1 actually does not work. It's useless. Because already this one already covered all of this. Okay? Right? Any question? So the so-called admissible set of those 4 parameters. Here we consider only 2 parameters, the acceleration zone, TS1 and TS2. In this example, the admissible set of T1, TS1, TS2 must satisfy this, right? So we look at the set of this, these 4 sets. And these 4 and 3 equality. And their relationship. We look at the boundary. Boundary meaning the equality. Okay. These 3, the boundary are 3 curves. Actually, 2 straight lines and 1 hyperbolic curve. Let us look at the relationship of this. There are 3 cases. The first one is like this. In other words, this is outside this boundary. We look at C1 and C2 first. Okay, their relationship. This one is outside this. Then you don't need to consider this for this, because this one will take over all of the constraint imposed by C1. Okay. And another case is that they have intersection like this. They have intersection. And they have intersection. Okay? If they have intersection, there are also 2 cases involved C3. Okay. One is that C3 do not have any intersection with C1. Okay, like this. Another case is C3 has intersection with C1, like this. Okay. And finally, if C3 is below, or C1 is larger than, so if you have let me open a new TS1, TS2. This is C2. Okay. And this is C1. Okay. Suppose C3 is like this. C3. And this is the C2. This is C1. Okay. C1, C2, C3. Okay. And remember, C1 should be C1 is the boundary of this, right? You need to greater than this. C2 is also, you need to greater than this boundary, so it's like this. So C2 is like this. So their intersection actually is this one, and their intersection is actually this one, and this. Okay. And however, C3 is what? C3 you need to less than C3. So these three sets do not have any intersection. So the intersection is empty. Intersection in this case is empty. So in that case, there are no parameters that you can choose. Physical meaning is that, is what I say. Is under this condition, you cannot design acceleration, S-shaped acceleration deceleration. Under this condition. Okay. Any question? So in order to find out the so-called feasible set, find out the feasible set, we need to find out the intersection points and the condition of case 1, 2, and 3. There are some complicated geometry and algebra manipulation. I will not go through the details. And the result is this. These are the necessary conditions for acceleration, deceleration of S-shape. Okay. In other words, remember, these are the given parameters. You have a given length. Here. These are the given parameters. You are given length, given maximum feed rate, maximum acceleration, and maximum choke. Okay, you are given this. Then you want to find T1 and TS1 up to TE2. Okay. So you are given this parameter. That means alpha, beta, gamma, theta are given. Okay. And the intersection, the so-called Q1, Q2, and Q3. Where is Q3? Q3 is here. Okay. Q3. Q1, Q2, Q3, this intersection point can be expressed in terms of alpha, beta, and gamma. Okay. And by this relationship, finally we can get a condition like this. In other words, these parameters, the given parameter, the constraint, and the given length, these parameters need to satisfy this so that you have non-empty unmissable set for you to choose the parameter. If you do not satisfy these conditions, then you cannot have S-shaped acceleration deceleration. Okay. So let us look at the physical meaning of this result. Okay. There are 3 sets, right? And the condition is that the intersection of these 2 sets, union this set, must be non-empty. So that means either this satisfy or this satisfy, then you have acceleration, you can have parameters and this for set. Okay, so let us look at one by one of this. A over 9 gamma squared less than beta z. So alpha let me do it here. Alpha equals 3L over L over VA over VA, right? Beta VM over AM. VM over JM. Data. Okay. And over 9 gamma squared. Gamma squared is beta z. Let us look at this first. What does this mean? Physically. Oh. Physically, what does this mean? Look at this. Alpha. Alpha meaning is related to L. So that means if L is very small, such that this beta is larger than this number. Let us look at a simple case. Suppose Vm is the same. Vm is fixed. L is small. That means your acceleration need to be what? Large enough. The constraint of acceleration need to be large enough. If your constraint of acceleration is small, that means you cannot have too large acceleration. Then you will violate this. In order to satisfy this condition, the acceleration limit should be large enough. Okay. This actually implies you need to have a larger power for your actuator. Okay. If your error is small. If your error is very large, that means suppose this number is very large, then most VM and AM will satisfy this. Then you don't need to worry about it. So this is one of the meaning. If the length is short, it's more difficult to have a S-type acceleration deceleration. Okay. And another meaning is that the VM. Okay. If your maximum velocity, remember this VM our condition is that we have to reach VM in a constant speed form. In other words, we have to reach this VM here. Okay. So if your Vn again for this condition, if your Vn, suppose these two are fixed, if your Vn is large, then this is large. This will become large. This will become small. It's not easy to satisfy. Okay. In other words, for a given length and a given An, if you have a large Vn, then this condition is also not easy to satisfy. In this case, you need to tune your maximum free rate smaller in order to have a S-shaped acceleration deceleration planning. Okay. So these are for this inequality, the physical meaning. And look at this part. This involves this. Okay. Beta and gamma. Okay. So this gamma meaning joke. Okay. Again, we look at this. Suppose Vm fixed. Vm fixed. Then beta and joke. If your joke limit is small, if your joke limit is small, that means this is large. Especially there is a square here. This is large. Then it's not easy to satisfy this condition for small joke limit. So the joke limit need to be large enough. Okay. So and for also for this inequality, we hope An is small enough. The acceleration is small enough so that it's easy to satisfy this. Why do we want to have a small acceleration for this? Small is relative. This so-called large and small are relative. Relative to joke. In other words, if you have a small joke, that means you cannot have large An. If you have a small joke, you need to have the corresponding acceleration limit should be also small, so that you can have a S-shaped acceleration deceleration planning. Okay. Any question? Okay. These are for this inequality. And for the other, it's mistake. Then this means this is incorrect. This is incorrect. Sorry, I have to check it. Take a look at this first. Okay. So we need to satisfy this. Alpha greater than or greater than or equal to 2 data. Data is big problem. So data is big problem. and alpha greater than or equal to 2 data. Okay. Alpha is error here. Okay. Your error should be large enough. Okay. This inequality also implies error has to be large enough. Okay. You can see this. The condition is that all this, the union of this or this, both of them require error has to be large enough. If your error, your length is too short, you cannot satisfy this, you cannot satisfy this either. That means if your length is too short, you cannot have a S-shaped deceleration plan. Okay. This is the implication. And also the Vn, if you want to have a higher speed, similarly like this. If you want to have a higher speed, this will small, alpha will small, then it's not easy to satisfy this and this. Okay. So if you want to have a higher speed and if you have a short length, the S-shaped deceleration planning may not be feasible. Okay. Okay. And data indeed. Okay. You see, because you satisfy actually Yes. Actually, this should be beta. As far as I remember, this should be beta. You see, this is a beta greater than this. This is a beta less than this. So either beta greater than this and beta less than this. If beta less than this, you need to satisfy this as well. Okay. And because beta less than this, so gamma is greater than beta. Next time I will make sure, I will tell you if this is beta or not. But as far as I remember, this is beta. So it's so in the second case, beta less than gamma squared. So that means gamma squared greater than 9/8 beta. So that means inside this is always positive. Okay, because it's greater than this, must be greater than beta. It's always positive. Okay, in this case, it's always positive. Okay, and so under this condition, gamma need to be large enough. We should not say this. Gamma, we should say that alpha greater than 2 data. So consider this. Alpha involves Vn and L. We have discussed L. Let us do the Vn. If Vn is large, this is small, and beta will be large, and gamma will be large. So this will be large. Okay. So if Vn is too large, we cannot set it like this. Okay. So these are the physical meaning. Okay. Any question? So here I have some short comments. If the feed rate is too large, or the limits of acceleration and jerk are too small, S-shaped acceleration will not exist. Okay. These are from this. So your setting of feed rate cannot be too large, depending on the length, on the travel length. If the travel length is large enough, then yes, it's possible to have a higher feed rate setting. But it also depends on the limits of the acceleration and jerk. Any question? So here, I just want to make sure that you have the understanding that this kind of acceleration, deceleration parameters cannot be arbitrarily chosen. They have some limitation. Actually, this is for S-shaped acceleration, deceleration. We have many of them. For example, for this one, you can choose the acceleration time and deceleration time, right? But actually, there are still limits on the acceleration. So you cannot choose too short of TA and too large of your feed rate. That will make the acceleration very large. If the time is short and this maximum velocity feed rate is large, this slope will be very large. In this case, it may not be feasible for your machine. Your machine has a limitation on acceleration. So this case is simpler. And it's easier to understand than S-shape. Okay. And this one will be even more complicated than S-shape because you have additional constant acceleration range. Okay. So I want to show, I just show you this. But the idea, the concept can be applied to other acceleration type. All of them, you cannot arbitrarily choose the parameters for the acceleration deceleration. There are some limitations you need to follow. Okay, you have to understand this. Any questions? So basically, these are from these three cases, a combination of these three cases. Finally, you can get these conditions. Any question? Next, I have introduced this and in chapter 1, I remember. So I will briefly review a little bit about the so-called block chain. This one is for only one block, one 9 segment or one arc or one freeform path. just one block. This is for one block. So for one block, if you just want to travel one block, then you will begin with 0 speed and end with 0 speed, something like this. But in general, for a path, we have in most situations, a complete path is composed of many so-called blocks. Many so-called blocks. So there is what we call block change. Block change. In other words, you want to go from one block to another, or one curve to another. This is what we call block change. Block change. And there are many different ways that you can travel from one block to another block. And for the commercial CNC controller, they also provide several options that you can choose. Here I introduce the one provided by Siemens. The first one is called exact start, and the second category is called continuous path. Exact start meaning that we start at a connection point, at a junction point. Okay. Let me see the example. Okay. So we go from the 3 blocks, for example. Okay. So this is the first block, N1, N2, N3, for example. The so-called exact start is that we start at the ending point of N1 and starting point of N2. We start here. Exactly. Okay. So this is what we call exact start. Exact start mode. Okay. In this case, we can reach the command point or command position accurately. But the pain point, of course, is that you have a long machine time. You have to go from here, start, and then go from here, start, then go from here, start. So each block, you have to pass through the acceleration zone, constant speed, and deceleration zone, start. Acceleration, constant speed, deceleration, start, and so on. So it will take longer time, much longer time for you to complete the whole path. This is exact start. Continuous path. Continuous path meaning that we don't want to completely stop. We don't want to completely stop. We want to continue. Continue. When we going through the so-called corner, continue. This is what we call continuous path. So we can avoid too much break. Okay? And allow each action to transit to the next block with constant speed. But of course, you cannot reach the command point accurately. Why is that? Let us look at these two first. Exact start and continuous path. Two different modes, block change mode. Okay? Exact start meaning that we will start at the command point, but there is a small option that you can choose here. The Siemens provide 3 different options. Exact stop find, exact stop cause, and interpolator stop, and interpolator end. Okay. This exact stop find, meaning that the block change is activated when the actual condition is within a small distance of the set condition. Okay. And this is the set condition. This is set condition. Okay? And suppose this is the motion direction. Okay? The motion direction. Okay? And within the neighborhood of the set point, we set a threshold distance for this and this. The so-called exact stop point is that we set a smaller boundary within the set point. As long as your actual condition go into this small range, then the next block can be activated. Okay? As long as you within this. The so-called exact stop cause is that this range is larger than this one. This is called. As long as the actual condition is going inside this range, then the next block will be activated. So that means, well, this is, suppose this. Let us enlarge this region. Enlarge this region. Okay. This is a set point. Suppose the actual condition is this is the command test, right? If the actual condition, this is the exact stop point. If the actual condition go inside this circle, then the N2, the command of N2 will be provided. Will start to provide. In other words, the block of the second block will be activated for the exact stop. Fine. For the exact stop cause is that as long as your actual condition is going to this, okay, then the second block will be activated. And finally, interpolator end means that as long as your command reach this point, the second command will be activated. So the block change is activated when the command for the present block ends. Okay. So when your command reach here, you begin the next command. Okay.
So interpolator, it means we stop, no?
Interpolator
And
end meaning that you do not consider the real actual motion. As long as your command reach here, you begin to provide the next command. Okay. This is what we call interpolator end. And these two, they will consider the actual condition. This one, we do not consider the actual condition.
but if we reach the set position, that means we have stopped.
Yeah, of course. Then it will stop here, and then begin the next. Okay. So it will be like this. You have acceleration, constant speed, deceleration. And you have acceleration, constant speed, deceleration.
So this is the case for interpolator and
Yeah.
okay.
Okay. But for the exact stop phi and exact stop cos, we have some, we will consider the actual motion. If the actual motion going to a small neighborhood or a larger neighborhood, then we provide this. But for all the exact stuff, their acceleration, deceleration also like this. They will start here. The command will start here. So this is the command. Acceleration, the constant speed and deceleration, right? So this is the exact. This is the what we call the interpolator end. When your command reach here, then you begin the next one. Okay. And this one is the interpolation cos, and this one is the interpolation. The exact stop cos, exact stop phi. You have to. This is actually the set, like the set point position. Okay, you have to smaller in the neighborhood of the set point. Then you begin the next step, next block. Okay. Continuous path mode, meaning that from here to here, originally the command is here and here. So a 9 segment followed by another 9 segment. Okay. We try to keep constant speed during the block change. Okay. So there are several options. This is the first one is called general continuous path mode, and this is what we call the programmable rounding. You make a circular arc instead of the sharp corner. Instead of a sharp corner, you follow a circular arc. Okay? And this circular arc, there are two different choices. One is called ADIS, not AIDS. It's ADIS. Okay? And ADIS pulse. Okay? This is like this. Okay? And this is what we call the setting, your setting. This is what we call ADIS, the rounding. The rounding. This is the programmable rounding. Okay. And so it's something like this. Something like this. So this actually means that you can specify. You can think of this. You can specify the radius for this. If you have a smaller radius, it will be closer to the sharp corner. If you have a larger radius, it will far away from the sharp corner. But the corner error will be larger. Okay. But larger radius meaning that you can have a higher speed. Smaller radius meaning that the curvature is larger. So you cannot have too high speed. Okay. We will continue to discuss this next week. Okay. Thank you.